All right, everyone. I'm Gang Chen. In this session, we're going to discuss FMI data analysis, specifically for task-based FMI. So let's look at the big picture. For each study, it usually involves 4 stages. So we need to design an experiment. So that's pretty important because whatever you're going to get out of the data heavily depends on how you are going to design experiment. Um, We're going to briefly discuss a little bit today, but maybe a little bit more on Thursday. So the next stage, once the data is available, we need to pre-process the data. So that will go through a list of steps about the quality control and how to align the data to the standard space, for example, smoothing, etc. So the third stage is about modeling. The modeling is currently the common practice is divided into 2 steps. First, analyze the data at the individual level, then move to the group level. So the reason we divide, of course, it's more practical because of the amount of data and also the complexity of the model building process. So that's why we split into 2 steps in terms of modeling. Once we have the data, the final results available at the group level, that involves how we report the results to write up the paper. Today, in this session, we're going to discuss the individual level data analysis. So that's about modeling. For modeling, there are typically 2 goals. The first is about the statistic inference. We want to see for FMI, we want to see which brain regions potentially involved the task we design. So that's called a statistic inference. So that's under the traditional statistics framework of null hypothesis significance testing, we use some statistic evidence. That's typically the p-value or statistic values to give us some sense about the strength of the evidence. So we say something about the evidence. For FMI, there are 2 major types of experiments. One is called task-based, the other one is recent state. There's the third category. It's a little bit less popular. It's called the naturalistic scanning. For task, usually we tend to make some causal inference. That means because we specifically design experiments with some tasks to manipulate the brain, to force the brain to respond to some specific tasks. So in that way, we can say to some extent about the causal relationships because we manipulate it, then we see some changes. So that's pretty much like the clinical trial. So we can make some causal inference. But for recent state, since we don't manipulate the brain, we just let the participants lie in the scanner. So it's a free-wheeling process. We can only calculate the correlations. So in that case, there's some ambiguity about the causal relationships. So that's one type of from data analysis, one approach. The other one is make predictions. That usually is like, for example, currently machine learning, but we're not going to cover that. So for statistical inference, the most popular approach is a localization. We say each brain region, whether it's that associated with the task, specific tasks. Suppose we have happy or sad tasks, we find out which brain regions are responding to each of those 2 tasks. Of course, there are other approaches like to say something about the brain networks. There are some methods, for example, structural equation modeling, dynamic causal modeling. Those have been around for a while, but it's pretty difficult. There are a lot of caveats. So for this specific session, we're going to talk about the FMI data analysis at the individual level. So we're going to briefly review the modeling. That is a regression model. Some people call it general linear model. That's probably GRM. That's a more popular term in the field. But in essence, it's just a regression model. So the model, we usually break into three types of components. So then first we have those are covariates. So the blue one you see here. Then the effects of interest. That's usually associated with the task, specific tasks. Suppose we have happy and sad two conditions. So those are the two tasks we are going to make a statistical inference. Then the third one is anything we cannot explain in the data, then that's basically the residuals. How do we construct the experimental variables, which we can say something about their tasks, effects? That is the concept of we need to understand the both signal. What is both signal, and how we're going to build a bridge between the stimulus, the task stimuli, the trials, and the hemodynamic response. So those are the components we need to understand before we build that bridge. That bridge in the field, if you have been in the field for familiar with the basics, is that that bridge is called hemodynamic response function, HRF. So that is some people call it impulse response. Assume there's a short period of event, right, like push a button, then presumably the both signal will have some sluggish response. That specific shape is currently called a canonical HRF. So that's a typical approach. That's pretty much almost everybody uses. But that approach has some caveats. So that's why there's another approach. It's called a hemodynamic response estimation approach. That is more like data-driven. We don't make assumption about the response shape. Instead, we use the data to estimate that response. There's something in between. That's SPM's approach. You have the basic canonical HRF plus a couple of adjustment about the shape. Then we have some miscellaneous issues we're going to discuss at the end. So let's briefly review the modeling, the regression model more specifically. Regression model is a statistic modeling technique. It was started about 140 years ago by Charles Darwin's cousin, Francis Galton. So he was interested in the relationship between the children's body height and the parents' body height. So he plot something like on the lower right corner, plot the data points, then he fitted that with a straight line. So that was how the concept of regression started. That straight line basically tells us about the association, right? It's not necessarily causation, but at least give us some sense about the relationship. That's the simplest case. We have two variables. One is the x-axis. That's called we typically call it experimental variable. The y-axis is we usually call it outcome or response variable. So if we write down the model on this, that's usually y equals beta 0 plus beta 1. That's then the x is the experimental variable plus the residuals. So that's the simplest model. Then we fade it with a straight line. The straight line, if we look at the slide, is have two parameters, right? So beta 0 is the intercept, right? So that's when the x is 0, what is the expected brain response, for example? Well, not necessarily brain response, but we'll say that's in fMRI we call it baseline. So that's the intercept. Then there's a second parameter, it's the slope. The slope is we can interpret it as a marginal effect. When the x changes 1 unit, what's the amount of change in the outcome in the response variable? So that's the slope. We usually write that model into this vector matrix format because it's more concise, right? So it's easy to manipulate using the algebra to express the solving process and also for programming. So on the left-hand side, the y, we put it as a vector, right? So for fMRI, that would be our time series at each voxel in the brain. On the right-hand side, we have the intercept. So the corresponding vector is just the 1, 1, 1. So then the second term is the time series for fMRI. right? So the beta 1 is the slope. So once we write this, we can uh, put express the model as the matrix format with a y equals x times beta, right? So the y is the vector of the response variable. X we usually call it a design matrix. More general term is called a model matrix. But for FMI, we call it a design matrix because we can largely manipulate that matrix. It's under our control, right? It's not just like a observational data. In that case, we would not call it a design matrix. For FMI, we call design matrix because we specifically design the tasks and the timing file that will pretty much fully determine the column, some of the columns in the design matrix. So once we have that model went into a matrix format, we can solve it, right? So that's if you still remember what you learned in statistics course, then that process is called ordinary least squares, right? So we solve it with this formula. So once we solve it, then since in more general case, the matrix, model matrix has multiple columns, not just one, as the simple model we showed, for example, from Francis Galton's case, not just two columns. In FMI, we usually have probably 10 or even more, sometimes 20 or 30-ish columns. So it's a big model matrix. But in the end, our interest is focus on those columns associated with the tasks, right? So suppose we only have two tasks, happy and face, we would focus on those two beta values associated with those two columns. But what are the rest columns and the associated beta values or the model parameters? So there are covariates, which we'll discuss. How do we include those covariates? That's the model process. So once we have the model, let's expand it instead of the matrix format. So writing into this multiple experimental variables. For FMI, on the left-hand side is the EPI, right? So time series. On the right-hand side, there are three colors. The blue one, the beta 3, beta 4 are, for example, suppose we only have two tasks, that would be our focus. That's people usually call it regressors of interest. Then the red ones, the beta 0 is the intercept baseline, then plus something. What are those something? That's for FMI typically like head motion, right? Or sometimes occasionally may have some physiological components. So the green one, the last one is the residuals. Anything we cannot explain, we just put it under the rock. So that's the residuals. So for task FMI, that's pretty straightforward, right? So we focus on the blue. Those are two, in this case, the two beta values, model coefficients. But for resting state and the naturalistic scanning, we also apply this regression model, but the model in the end, it's not those model coefficients we're interested in. Instead, in those two scenarios, we use this model as basically a denoising process. We move the stuff we are not interested in. For example, motion, physiological components, right? So in the end, it's the residuals we care about. So that's why I say the model is used as a denoising process. That's for recent data and naturalistic scanning data. So once we have the model, we solve it, we get the point estimates, right? So those beta values, usually we put a hat in the notation, a beta hat. So that hat means that it's the estimate, right? So you will get a one number, whatever the number is, it's just the estimate. So in reality, we don't know the true value, right? So in addition to that estimate, there's an uncertainty. That uncertainty, if you remember what you learned in statistics, that's called the standard error of the point estimate. So Ideally, we should have those two. One is the point estimate, it's just single number. Then there's the uncertainty. This uncertainty is called the range. That range is standard error. But under the traditional statistic framework, people are more interested in the so-called statistic and the p-value, right? So that's just one perspective and the dominant perspective. But another perspective, personally, I prefer is focus on the estimation instead of a decision-making process using the p-value. Why is that? We can elaborate a little bit later on. But let's currently focus on the traditional statistical framework. We have the point estimate, then we have t-statistic. What is the t-statistic? T-statistic is basically the point estimate, the beta value, estimate the beta divided by the standard error. The standard error is the uncertainty, right? Or you can say it's the precision. Basically, how precise the estimate is the reciprocal of the standard error. So the t-statistic value also tells us to some extent about the uncertainty of the point estimate. So, well, intuitively, we have a lot of experimental variables, right? So we have the experimental variables, the task associated with regressors, and also we have a lot of covariates like head motion, right? Estimated head motions. So those regressors, intuitively, we can think of they are tangled together. Right? Ideally, if they are well separated, it would be easier to disentangle them. But what do we mean when we say we disentangle them or they are tangled together? That the concept or notion is usually, you can say, the collinear. How are those regressors correlated with each other? So if they are less correlated with each other, it would be easier to separate them, right? But in reality, they are correlated to some extent. So then the question is it a good idea to design experiment that we can much easier to separate those regressors? That's intuitively that would be the answer would be yes, but in reality, it's more complex than that. So usually it's a concern when we say they are collinear across the regressors, but it's more subtle. We will probably come back at sometime to discuss that later on. So once we have the model, then how good is our model, right? So that depends on what we put into the model, right? So how do we create the regressors? So that's more essential. But in the end, once suppose we have built our model, then so we estimate those model parameters. There's some couple of ways to check the quality of the model. The one way in the traditional statistic, we have this, sometimes we call it omnibus F statistics, right? That F statistic tells us about the overall among all the regressors, what's the statistic evidence, how much you can explain. Probably most, little bit more explicit is the determination coefficient. That's R squared. That's need to be from another angle. That's basically the percentage of the variability that can be explained by all the regressors we're interested. We put it in the model. So once we have solved it, then we need to make some statistical inference, right? So the traditional statistics is more like a decision-making process. Why is a decision-making process? For example, suppose we focus on one particular task, this beta 3, right? So that's suppose it's the hemodynamic response responding to a happy phase, for example. So at each brain region, we get that beta parameter estimate. But the way we do it in the traditional statistics, we pretend it's 0, right? Of course, we don't know the true beta value. We pretend it's 0, then we get the t-statistic. If the t-statistic value is big, then p-value is small, there's a magic number 0.05, for example, then you can say, oh, I have strong evidence. So we can feel comfortable to declare, or more accurately, we can reject the null hypothesis. So we can see this brain region is, we have strong evidence to show that that brain region is engaged under that particular condition. But usually in fMRI, we'll not just focus on one particular task. We usually compare two. For example, we want to see that brain region, whether that brain region is more engaged under happy than under a sad condition. So for example, in this case, beta 3 versus beta 5. So the null hypothesis, we pretend there's no difference between those two task conditions. Then we get a t-statistic value associated with the ideal null hypothesis. So then we go through a similar process, make a decision. Right? So that's the traditional statistic. There's occasionally we may say we want to average between two conditions versus the third one. For example, have happy, sad, and neutral. So we get the average between happy and sad, then compare the average to neutral. Right? So that's one possibility. Occasionally, you may have some we call it a compensating null hypothesis. Suppose three conditions, right? So happy, sad, and neutral. We pretend there's no difference across all the three conditions. So then in that case, t-statistic value is not good enough. We would, in this case, use a F statistic because it's not just compare two or a single one. Then we need to compare pairwise comparison combined. Or even more, a little bit more specific. We will say all the three are equal zero. That's another possibility. So all those two, both those two cases, we can use a F statistic to make assessment about that null hypothesis. Then one thing I want to say about the fMRI, the typical approach is called a massive univariate analysis. What does that term mean? Well, we pretend the brain, we when scan the each brain, we get many voxels. Usually it's probably, for example, 200,000 voxels. We don't treat the whole brain as a single unit. Instead, we pretend each voxel is unrelated to its neighbors, right? So that's why it's called a massive univariate. The word univariate is a little bit misleading because normally the word univariate in statistics is that we only have, on the left-hand side, only have one variable. So in this case, the reason we call it massive univariate because we pretend the voxels are unrelated to each other, especially among the neighboring voxels. So in other words, suppose we have 200,000 voxels, we build 200,000 separate models. So we analyze each voxel separately. There's no communication among those voxels. That's a big assumption and it's false, but currently we have to live with that assumption. That's why, especially when we go to group level, this is troubling. As people call it multiple comparison problem or multiple testing issue. That's why the field struggle with this issue. That's because this assumption, we started with the assumption that is false. That's why we pay the penalty. That penalty is heavy. But that's for a couple of reasons we have to adopt this approach is because computational complexity that we will talk about on Thursday, whether there's an alternative to improve that approach. But let's start at this moment. Currently, we just discussed this massive univariate. We analyze each voxel separately. So now let's switch to some terms, some concepts about the fMRI. So fMRI, the big picture, we usually recruit, when we design an experiment or study, we need to recruit some number of participants, right? So we need to decide how many we want, right? Whether we have one group or two groups, right? So suppose you have patient group or you have a control group, right? So that's, you need to decide groups. overall, or each group, how many participants. Then there's some construct like tasks. Suppose it's body emotion, positive, negative, neutral emotion. So three task conditions. So those are big picture. Once we have that big picture, well, even in some more challenging is you may have two factors. Then you need to focus on interaction between two factors. Right? So that's even more difficult. But let's say just a simple task with two simple three tasks, happy, sad, and neutral. Then for each task, there's also sample size. We need to show each participant some number of called trials. So each task has some sample sizes. So that's the concept of trials per condition. Then we need to decide whether it's a block eventually design or sometimes it's a mixture of the two. So what is block and eventually design? Well, block means is basically each trial lasts for some period of time, for example, a few seconds or even more. That's called block design. Eventually design, usually the duration of each trial is relatively short, for example, 2 seconds or less. So that's the reason we differentiate the two is probably for more modeling purpose. But there's also consequence in terms of statistical inference because block design can be considered as a special case of a trial eventually design. We can consider each block as many trials jammed together, right? So purely from statistical perspective, block design is probably much better in terms of statistical evidence. But that's just the statistical perspective. In reality, for each study, we need other considerations. For example, if a block design, we tend to get fatigue or attenuation. Well, you are familiar with the participant is familiar with the tasks. After a while, then the brain regions don't respond as strong as expected. Then that attenuation is problematic, right? So nowadays, probably most of the time, people adopt the eventually design, not just for statistical reason, more for cognitive reasons. Then there's once we have decide the number of trials, then there's a term called interstimulus interval. Some people call it intertrial interval. So that the concept we have that is because we want to randomize the sequence cross tasks and jitter the intervals. That's for a couple of reasons. For statistic reason is that will be less correlated with each other among the variables, regressors. Another reason to avoid the anticipation. That's not for statistical reason, but for cognitive reason. So we want to avoid the anticipation. So then there's other concepts like TR. TR is basically the time interval between two consecutive volumes. We scan or acquire the data from the scanner, the voxel size, total of data points. Right? So that's a number of TRs. Then there's other parameters. Then, this slide is about the difference between block and block design versus eventually design. I already briefly discussed on the previous slide. So nowadays, we pretty much focus on eventually design, not because of the statistical consideration, more about other perspectives such as a collision, avoiding fatigue, avoiding anticipation. Next, once you have some basic understanding about the fMRI, now we need to build the model. Right? Before we talk about the modeling, I create this slide. It's a new, you don't have it, but in your PDF file, because I just created this morning, a couple of hours ago. I think this, I hope it better help us understand the challenge of fMRI data analysis. So as a good and bad and challenges, what is good? Well, the blue part is what since we are talking about the task-based fMRI, so we ask the participant to perform some tasks. So more specifically, each task has some number of trials. We call it stimuli. So each stimulus that it triggers the brain response. The brain response is in each brain region is the neural activity. That's usually spikes, right? So that's many spikes. So the information flow goes, so the chronological order is we have the task, the stimulus, then we have the neural activity, then we have the hemodynamic response. What is hemodynamic response? That's the physiological part, right? So the neural activity triggers the blood flow, triggers the oxygen content in the blood. And that is a complex process. Depends on how we characterize them. Can be the blood, how fast or slow the blood flows, and how much oxygen content in the blood, right? So that's and also involves the neurovascular structure, right? How many, how intense or how sparse the blood vessels in each brain region. So it's a proxy, complex physiological part of this information flow. But we cannot characterize the hemodynamic response fully. We can take a snapshot. That snapshot is the both signal. That's where the scanner can read. That part is both basically stands for blood oxygen level dependent. So that we can, from that angle, we can see something about the hemodynamic response. But even fMRI is not fully about the both signal. It also contains noise. That brings us to the this second causal path, another part of this path. So that is the noise, whatever we call the noise. What is the noise? There are many components. For example, physiological. Each time the participant responds to the stimuli, they may triggers the heart may beat faster, the breathing, right? So that may, because you need to respond to each stimulus. So there's a physiological response that may trigger some head motion, or there even independent of whatever the tasks, there's thermal fluctuation in the scanner. Or so that's also itself is a little bit challenging. So from the beginning, the blue part to the end, the red part, that's our causal path, right? So that's how the information flow. So whatever I put the dashed boxes, those are I call it latent components because we don't know, we have no idea. So we have the blue part, the red part. In the end, I mean, ideally, we would we would really like to say something about the neural activity. Unfortunately, we cannot, right? Because we can only say something about the signal. Well, before we can say something about the signal, those are noise that can contaminate the signal from a signal. How do we remove as much as possible as the noise? That's one challenge. The second challenge, even if we can take care of the noise, there's still challenge. That bigger challenge is about we cannot 100% sure say something about neural activity. We hope the both signal can say something to some extent, say something about neural activity, but that to some extent currently is pretty weak, right? Even a couple of months ago, there was a paper that declared that that paper basically says 40% of the brain voxels, the relationship between neural activity and the both signal is maybe inversed. What does that mean? That means when the neural activity goes up, the both signal may goes down. But that paper, I think they're still pretty controversial, and some people don't agree. There's some caveats. So you can see, even though the fMRI is a wonderful tool, but there's a big challenge. That big challenge is we cannot 100% sure say something about the neural activity, even though probably we would agree, say, well, to some extent, but at some extent is between 0 to 100%. Where that is, that pretty much we cannot say where that extent is currently. But so that's the challenge we face. Let's just ignore the neural activity. Suppose we want to focus on when I was stimulus, can we say some both response? That even for that, we need to say, face the challenge of the noise, how to characterize the noise. That brings up to the next slide. So that means from a signal on the left-hand side, that's the data from the scanner. We hope we can separate the signal from the noise, right? So that's our hope. Well, the signal is basically, in this case, the both signal. Both signal, that's, suppose we have two tasks, happy and sad. Then the noise. Well, as I mentioned earlier, the noise can be thermal noise. That's usually random fluctuation. That's usually, it's okay, right? Because it's random, we can more comfortably, say it's follow Gaussian distribution if it's, suppose it's white noise. The more challenging is about the physiological and the motion, right? So that's why in the model, the signal part, in addition to the signal at the bottom of this slide, is the Boda response. We also need to inject those blue components. The blue components, there's baseline, right? The intercept. Then there is slow drift. What is slow drift? Slow drift can be physiological or can be thermal, right? So that's, we don't know. There are components. We just usually use, it's called a slow. That means the drift. So usually in FNA, we use polynomials to characterize the slow drift. In other software packages, they use some frequency band, right? So I believe it's like 128 seconds is their cutoff. So anything longer than that, 128, they use cosine, for example, to capture that slow drift. You can say that 128 is some fudge number, right? So it's not some magic number. We just believe that will sort of capture the slow drift. Even we use polynomials. Even with polynomials, we still need to decide the order of the polynomials. We use linear, quadratic, cubic, so we need to make that decision. We'll discuss that later. So then the other effects of low interest, other covariates, the most popular one is the estimated head motion. Well, even head motion, we cannot pinpoint what is exactly head motion. We have to estimate. That is done during the pre-processing. That estimate motion is still challenging. Why? Because probably tomorrow we'll discuss more in detail how those head motion components are estimated. There are usually typically 6 components. When we put in the model, immediately we need to assume it's, suppose we just adopt those 6 components, we assume it's linear, right? So whether it's linear or not, nobody knows. So that's why sometimes people put more than 6, for example, 12, or sometimes even 24, use their the derivatives, first order, second order, then I hope when you include the number of components, the hope is you can capture some nonlinearity of the head motion impact. So that you can say the modeling will just try as hard as possible, but in reality, how good that is, we can tell that by the noise. So later on, probably tomorrow, when we use the wheel data, you can see the amount of noise. That's basically, especially we use the determination coefficient, the R square, the percentage of all those variables can explain. For I from I, that percentage is pretty low. Probably the worst, probably 10% or 20%. That's probably pretty typical. So that tells us how much we understand about the signal. That's why I feel this diagram helps us to understand why FMI is so challenging, FMI data analysis. So I forgot to mention there are 2 paths, the arrow flows, right? So there's a bottom one that's what we care about. The upper one, it's also, it flows because it's embedded in the FMI signal. So that's contaminates the signal we care about. So even if we take care of that, we still face the challenge. We say something about both signal, but how is that related to neural activity? We hope that's strongly associated, but there's still challenges, and it's to pinpoint that relationship. All right, this you already saw previously in Paul's presentation. So let's start with a simple case. This is we usually call it block design, even though nowadays we rarely use block design, but as a basic understanding, it's a good example, right? Suppose in this case, the block design is we have 20 seconds on, off. Suppose just ask the participant to push button for 27 seconds, then take a break for another 27 seconds, right? So in that case, the width curve is we call it a regressor. Suppose it's just a simple task, right? So it's just either on for 27 seconds or off 27 seconds. So suppose we somehow create this width curve. We call it a regressor. So it's just simple one task, right? One task. How we're going to create that, we're going to talk about it later. But suppose we come up with this we expected response in the brain region. So we use that as a ruler to search the data. The data is the width curves, right? So it's a zigzag because it's a discrete. The TR is 2.5 seconds. So that's why we say the zigzags. So we use that width curve to search the pattern, use as a pattern to search, and then fit the data, the black curve. Then we come up with the blue curve. Well, the blue curve is a little bit different, slightly different in terms of the shape, right? Different from the width curve. Why? Because it looks at the downward drift. The reason is this is the fit, how much we try our best to fit the data with this blue curve. The blue curve is the width curve scaled, of course. That's the beta value. Plus, remember the model, there's a baseline, there's slow drift, and other effects, usually the head motion, right? So that's why the blue one is the width curve scaled plus any other covariates we could put in. So the width curve is basically the performance, how good the model is. So that's block design. We can clearly say the pattern because it's each trial or each block is well separated. But that kind of a design is not efficient because we probably waste too much as the 20 seconds off. And also that's, as I mentioned earlier, block design is not a good idea for especially we want to avoid habituation in attenuation. So that's why nowadays pretty much all the time people are use event-related design. So in that case, even if we have a single task, we need to randomize them. Randomize in the sense in fMRI there are two notions. Even with a single task, those trials, we jitter their intervals between consecutive trials. That's one notion of randomization. Another one is when we recruit participants, we also need to randomize. Presumably, we need to randomly choose those participants from the pool, the big pool, the whole population. In reality, probably we choose from on college campus, we recruit from students. Not really, that's more convenient than from the bigger population outside of the campus, for example, more weighted. So in this case, suppose we have randomized the trials. That's why you see the red curve at the top is there's no clear pattern, right? So we randomize some trials are more closer than others. For example, there's a big, for example, here, this big pump, that means those two trials are right next to each other. So that's why they superimposed. And the first three, sort of separated from each other, you can see there. So that's why eventually design, it's difficult to use that pattern visually to match the real data, the back curve here, right? So that's why we have to use some other ways to make assessment about how good the bad fit is. So the upper one, lower one, if we only focus on the blue curves, it's hard for us to I mean, visually tell whether that voxel is engaged or not. So, but the other index, for example, we use the correlation or the beta value will tell us to some extent. Then we need to move to now the notion of how do we create those regressors, which we care about, associated with the tasks, right? So that's we need to bring up the notion of hemodynamic response, hemodynamics with function, and then once we have those concepts, then we how to create those regressors. I believe it's time to take a break, 10 minutes break. So let's stop here, then come back 10 minutes later, 11:50. All right, let's pick up where we left. So I want to revisit this slide a little bit more before we move forward. So I want to say a little bit more about the difference between hemodynamic response and Boltzmann signal. So hemodynamic response is the physiological part. So that's more like a fluid dynamics, right? But it's physiological. Boltzmann signal is more about physics, what the scanner can detect. So that only captures part of the hemodynamic response. So we need to make that distinction to understand the relationship when we move on to build the model. So let's move to here. We need to create the regressors where we care about that are associated with the tasks. So hemodynamic response is basically the physiological component, right, in the information flow. But FMI can only see part of it, that process. So that term is a little bit probably inaccurate. I mean, it's usually we say hemodynamic response, but in reality, we can only capture part of that, which is the blood oxygen level, right? So that's why the Boltzmann signal probably is a better, more accurate characterization of the data information. So hemodynamic response is the physiological component. I mean, in that information flow diagram. But there's another concept, hemodynamic response function, HRF. That's a more popular term or acronym. So that what is that? That is a mathematical characterization of the hemodynamic response measured by Boltzmann signal, but not just that function, not just the any hemodynamic response, a spatial response. What is that spatial? That is associated with we call it impulse response. What does that mean? Impulse, that means we give the participant instantaneous stimulus, like a short period of time, like for example, 1 TR or less, right? So 2 seconds or less, we consider that's pretty short enough, right? So for example, push a button or respond to something shown on the screen for a short period of time. So we call that the impulse response of the neural activity, right? So, well, technically we mean it's instantaneous without any duration, but practically we say it's a short period of time for the each stimulus or each trial. So the hemodynamic response function is the mathematical characterization of the hemodynamic response to that idealized each stimulus. So that's really clear about that, because that distinction or description helps us understand why we create the regressors the way we're going to describe. So once we have the concept of hemodynamic response and the hemodynamic response function, now let's consider a simple and straightforward approach to build a regressor for each task, right? So that's called a fixed shape or canonical HRF. So in the field, SBM started the curve on the right-hand side. It's called a canonical HRF. So it's a curve, has a special shape, right? So suppose, remember this, we consider it's an impulse response associated with the instantaneous stimulus. So that's the red arrow, upward arrow we see here. So that curve is, you can see it goes up quickly. Well, not quickly, I mean, it's depends on what time scale. Then slowly recover, right? Not just the way it goes further below the baseline. So you can see that's called undershoot. Then even much slower recovers to the baseline. So in SPM, this curve, the duration is 32 seconds, right? So the peak occurs at 5 seconds, exactly 5 seconds. So the recovery part is about, I think, 11 seconds, and that will reach the baseline, then goes further down, then we call it undershoot. Right? So why it's like this? Well, we don't fully understand currently why the curve is like this. They just early days based on motor cortex or visual cortex, we come up with this curve, I mean, in SPM. And in reality, some brain regions, there's argument, there's an initial dip. So even at the beginning, it goes below 0, right? But currently we ignore if we use the canonical HF. So that's one approach, one curve. In Anthony, there's another one, it's called the gamma variate. It's based on the mathematical function gamma variate. So similar, but it's shorter. The duration is about 16 seconds. It also peaks about around 5 seconds, but there's no undershoot. So that's a difference. And it doesn't have an initial dip either. So in Anthony, that function, you can say the mathematical expression is like this. The exponential component, right? So there are some constants. To those constants, for example, 8.6, then there's a 0.547. Do they mean anything? Do they capture any physiological mechanism? No, not at all, right? So they don't have the similar meaning like gravitational constant, for example. No, there's no such we don't have such an interpretation. In this case, we just do empirically based on the data recorded through different venues. So those curves are empirical curves. How good are they? Well, that's a big question mark. We'll come back later. Let's suppose we adopt whatever the curve, and we may need to make an assumption. That curve is the same across the brain, across all participants, regardless their age, for example, or the males or females, right? And so that's the assumption. Or also regardless what kind of tasks. So this we call a standard curve. Whether the brain response, how much is that the brain response is depends on the accuracy of this curve, and that response, the parameter beta value is the scaling factor. So that's why whenever we create a regressor, this is our ruler. So we make the peak as 1. So the beta would be interpreted as percent signal change, for example, if we pre-process data properly, but that's usually the Anthony approach. In other software packages, they don't necessarily scale the hemodynamic response curve as 1, even if they do, because they don't pre-process data the way differently from Anthony. So their beta values are not interpretable. That's something we need to keep in mind. So that's why pre-processing is important for many reasons. One of them is in Anthony is called scanning. So to divide each voxel's data by some number, specifically it's a local mean average across time. So that step allows us to interpret the beta values as a percent signal change, approximately, at least practically, that's good enough. So that's the concept of a hemodynamic response function. So remember, that's is associated idealized case. It's an impulse, instantaneous stimulus, right? In reality, of course, suppose we have 5 consecutive trials or stimuli like this. Those are 5 red arrows. So they are right next to each other, equally spaced, right? So how do we construct a regressor? Basically, that mathematical process is called convolution. It's similar to multiplication, but we can basically conceptualize like that. It's sort of like a multiplication. So it's a superimposed intuitively. So that's why we have those 5 color hemodynamic response function, as we show at here. But since we have those 5, we need to superimpose them. That's why I end up this black curve. So that's basically the summation of those 5 individual hemodynamic response functions. Sometimes we call it impulse response function. So that's, suppose we have 5 trials like this. This can be considered as well, you can see 5 events, or we can see a block design with a duration of, in this case, 4 seconds. It probably doesn't matter much because whether we treat it as 5 separate events or a block design, since they are so jammed together, it doesn't make, practically it doesn't make much difference. But of course, we don't, if it's really event design, we don't design it like this. So we would randomize their inter-trial intervals. So in block design, in this case, suppose each block will have 20 seconds duration. So under the equally spaced, even though that's probably not recommended because we're not randomize them, but it's just for explanation, for illustration purpose. Suppose we have a design like this: 20 seconds on, 10 seconds off. We would have go through this convolution process, superimpose those. I mean, each block, 20 seconds, we can consider is many trials, right, under each block. So the convolution process will end up giving us this black curve. So that would be our regressor in this case. Definitely how to implement this practically, I mean, probably tomorrow we will cover that, how to specifically in scripting, white script, or how to specify this process. So that's block design. Eventually design, suppose we have 4 trials like this, those 4 colored arrows, upward arrows. So we, again, the convolution process end up with the black curve, right? So it's the summation of those 4 dashed, dotted curves. So that's, as a user, you don't need to do this convolution. I mean, this is a mathematical process. So the program, definitely this is 3D convolve is the program name. That program internally will handle this. So as a user, you only need to provide the location, the temporal location, those arrows where there's a timing, right? When each trial occurs. So that's the input file. The program internally will perform this convolution process. Then in the end, you will get this black curve. So that's, you need, as a user, you need to pay attention. When you go through quality check, you will be able to visualize each regressor. In this case, would be the black curve. So let's back to this heuristic expression of the modeling process. Right. So the measurement data on the left-hand side, we decompose into 3 bigger chunks. Right. So the blue one is the covariance. Right. So typically we have the baseline, right? Regardless, even if we put a dummy in the scanner, we'll have the baseline, right? So the baseline is not 0, it's some number. Usually it's between 1,000 and 2,000 for typical fMRI data. So there is drift. That's because physiological or thermal drift. Then we have the typically we have head motion. That's the head motion components. So that's the blue part, which we consider as the covariance. Then we put the regressors we just created, use the timing file through the convolution process, put into that is the red component. Then anything else is we left it, we call it residuals, because that's we cannot explain, we just put it in residuals. So once we have that, then one thing I would like to mention is how to model drift. I mentioned earlier in SPM and FSO, they use the frequency, right? So cut it off at 128 seconds. Anything longer than that, they consider as a drift, right? So use the cosine, for example. So in Anthony, we use a little bit different. It's a little bit similar. We use polynomials, but one thing we need to decide is the order of the polynomials. So here I show a quadratic, but how do we decide? Well, let's just use the rule of thumb. So instead of using 120 seconds, definitely the rule of thumb is use 150 seconds. So if the scanning each run lasts for 150 seconds, we would put a linear. So instead of a quadratic here, we would move the quadratic term. If it's from 0 to 300 seconds, then we put a second, the second order polynomials. If we have, for example, 450, so then we use cubic in that case. So that's how we determine the slow drift. So once we build the model, then we can visualize how the model matrix looks like, right? So remember, we adopted this massive univariate approach. So we write the vector matrix format is y equals x. X is the model matrix times beta plus residuals. If you look at this model closely, the X, we call it design matrix. Each column in the design matrix corresponds to experimental variable. That experimental can be the intercept, the baseline, or can be one of those covariates, and also include the regressors, right? So let's look at the visually check the model matrix. The one popular way is to use this grayscale to show the model matrix. So the way we interpret that this grayscale image is like this. Each column corresponds to experimental variable. Each row is the time, right? So from bottom to top is from beginning to end, right? Suppose we have 150 time points. The first one would be at the bottom, the last one, the 150, the TR would be at the top, right? So that's the vertical is the y-axis is the temporal axis. So horizontally, those columns are basically those are experimental variables. So in this particular case, in Affinity, the last 6 columns here, in this case, is the estimated head motion components. Right, 6, the typical one, the 3 shifts, then the other 3 are rotation angles. So that's the typical way we characterize how much head motion. That's the last 6 columns. The first, in this case, 6 columns, you can see, let's focus on the first column. First column, I have fully black, totally black for the 1/3 of it. The last 2/3 is totally white. What does it mean? In this case, because we have 3 runs. What is a run in scanning? When we scan each participant. A run means it's a consecutive scanning, continuous scanning without break. We keep scanning, for example, for 10 minutes, right? Then there's a concept of multiple runs. Why do we need multiple runs? Why don't we just scan continuous all the time? From beginning to end. Well, that's the practical reason is there's a fatigue, right? So there's a amount of a tolerance each participant can sustain in the scanner. So usually we take a break for a few minutes, sometimes even come back later, after some days or even month, depends. So that's called a session. But each run, multiple runs, so we take a break, then the participant still stays in the scanner. For example, a 5 minutes break, then we resume the scanning. So that we have multiple runs. In this case, we have 3 runs. So that's why the first column, totally black, that means horizontal, that's their baseline. This is different. The concept of how do we construct the model matrix or design matrix is different from SPM and FSL in the sense that in Affinity, we have the option that you can glue all the runs together to build a single model. In FSL and SPM, they can only allow you to analyze each one separately. Right? So I'm not saying FNE does not allow you to do that. So in FNE, you have the option. You can analyze each one separately, or you can combine them. Usually we call it concatenate them. That you have the option. So if you want, you can analyze each one separately. Most of the time, it's probably preferred to concatenate them. That's why the reason is when we go to group level, we usually don't care about each one separately. Yeah. So even in FSL and SPM, in the end, they still you get the average across runs. Right. So definitely, if that's the case, you why bother analyze each one separately? So you can. That's why concatenation is the process. Under some circumstances, probably you do want to analyze each one separately, but that's at least that option is available in FNA if you prefer. Probably there are some special cases you do want to do that. For example, one case, one possible scenario is that you want to compare class one differences. If you want to say such a heterogeneity, that can be done. So in this case, back to the design matrix. First column, so since we have 3 rounds, that's one because we stop the scanner, so the linear drift, the baseline is different across rounds. So that's why we need it for the first 6 columns. Why 6? That's another question, because in this case we use the linear drift. We just use linear, the first order polynomials. We don't go beyond we don't have a quadratic or cubical. So that's why each round will have 2 terms. Is the baseline. Then that's why the second column you see the first third is this gradation part, right? So the first column, the 2/3 of the rest is white. That because we don't have baseline, because for each round, the first round, the baseline is only for the 1/3. The rest is we don't need to model it. Similarly for the second column, right? You may wonder the second column, the rest of the 2/3 is not white, unlike different from the first column, right? That's because I believe it's a centering cause that artificial, difference. So that's the first 2 columns. They correspond to the first one. The third column and fourth correspond to the second one. So you can see the black band shift to the second part, the second part of the 3 segments. Similarly for the linear drift, right? Same thing for the 5th and 6th columns. So then we shift to the last third of the third one. Okay, so those are in this case, is the baseline and the linear drift. So the last 6 columns are the covariance. In this case, head motion, estimated head motion. So in between, the 7th and the 8th are the tasks. In this case, block design, you can see clear the pattern, the black bands. So those black bands basically are those blocks. Right? So there's a block design, right? So let's check another way to visualize this. Probably FNE is specific. Another way to check the model matrix, instead of using grayscale, we plot out the time series or the pattern, right? The pattern, instead of using grayscale, we use use the curves. So let's move discuss from the bottom up to the bottom, each row. So now the model matrix, the columns are shown as rows instead of columns as in the previous slide. So here we show each column as a row because we want to show the time series as the time as the x-axis. So now let's look at the bottom one. The first one, the black horizontal line for the 1/3, the rest 2/3 is nothing, right? So that's the second one is the linear drift. So this is the upward slope, then the rest is 0. So now it clearly explains why the rest is on the previous slide. This second column is why is a gray instead of a white. That's because you can see that this horizontal line is 0, is in the middle of the linear drift, right? So that because it's centered. So third or fourth for the second round, fifth and sixth for third one. So the seventh row and the eighth row are those two regressors, right? So now you can see a different angle to check the regressors. So they are block design. You can see the pattern, right? So the different way to visualize those columns. Lastly, the top 6 rows are those estimated head motion, right? So probably the first 3 from the bottom up, those are that would be 9th, 10th, 11th are their shifts. You can see here there's a look at this blue curve. There's a big drop. That's a head motion, right? So you can from this way, it's from the previous slide, it's hard to tell, right? So I mean, it's the grayscale. It's very hard. So this way, I think it's at least the different angle and it's probably better. Personally, I prefer this. We can see clearly see the pattern or head motion, whatever. So that's in Anthony, we have this during the quality control process. You will see a lot, quite a bit later on, probably tomorrow, how to go through this process. You don't need to generate those curves. This is pretty much automated during the quality control. So which will be covered tomorrow. Another way is more from statistics perspective is that there are a couple of ways. One, there's a check how correlated those regressors are, right? So there's a warning, but probably there's don't be too overreact if you see some warning. On this, you have better idea. I mean, sometimes it tells the correlation, how correlated are those regressors. I mentioned earlier a little bit about those regressors, how on the one hand, we don't want those regressors to be highly correlated, right? So because less correlated, it's easier to solve it, to separate these, entangle them. But there's a downside. If we want to be equal, I mean, less separated, then we pay the cost. What is that cost? We would have to design experiment with those trials will separate with each other. That means the trial sample size becomes less small, right? So we pay the cost in terms of the trial sample size. So there are two opposing forces here. One is about the correlation, right? People call it collinearity. The other one is the number of trials. Those two opposing forces, which one is more important? I think now I think there's a better understanding. I think we would better pay the cost of the collinearity. Even if the correlation is as high as, for example, 0.95, even that, probably we're still willing to pay that cost. Then because with that cost, then we can increase the number of trials. So that's one angle to understand the counterbalance between those two opposing forces. Of course, there are sometimes we make a mistake about the timing files. Suppose two tasks, we made a mistake, then the timing file messed up. For some reason, we instantly create two identical timing files. Of course, that's collinear. That's 100%. The correlation would be 1. Of course, we cannot even solve it. That's like 1 divided 0. Okay? So in that case, it's not about the experiment design. It's about the human error. In terms of experiment design, sometimes, I mean, complex design, for example, you have a queue, then immediately the participant need to respond without any interval, right, in between. So that can be challenging, but even in that case, it's not desperate. We can still manage to handle it. We can even separately model the Q period, Q and the response, the participant response, even if there's no interval under some circumstance. We can talk about it later. So that's one way to check the model quality. This is more about whether it's a human error or it's some design consideration. So next is about the F statistics. So this, I believe, is definitely unique. So in the output, by default, you will be able to see the full statistics values at each voxel. So that full statistic, the full maybe it's a little bit ambiguous because in traditional statistics, the full is about all the variables. But in Anthony, this is not about all variables. It's only about the regressors of interest, especially about the task regressors. That's why I showed even though it's called a full statistic, it only focuses on the regressors, the task regressors, the weight part. So it's that model versus the model without that. So when we compare those two models, the F statistic tells us what's the weight part, the importance of that part, how much it can explain. So that's the full statistic. Of course, we want that value is big, the bigger the better, because that explains the amount of information in the data. So another component statistic is called a determination coefficient R square. That's a percentage. So that suppose it's 50%, for example, at the voxel, that means the task effects can explain half of the data variation. But for event design, that number is pretty low, unfortunately. But we have to live with that fact. We also have the faded curve. That's, as we saw earlier, that the blue curve. That's basically all the variables we can put into the model, including both the task regressors and those covariates. So that's the option called the fates. That's a fated result, fated model. Then there are residuals. The option called the ERRTS stands for error time series. Basically, whatever we can explain, it's there. So that's the residual part. So during quality control, you can visualize those two time series at each voxel. Well, once we have the beta values, estimate the beta values, right? Those are point estimates. It's a single number at each voxel for each task. So now we need to focus on, most of the time we focus on the contrast or comparison between two conditions. Right? Occasionally we do some case there's a composite condition. For example, here we have happy side average versus control, neutral. That's occasionally you may have something like that. All right, so that's the simple approach. That's the currently most people use almost all the time. This approach we assume a standard curve, that hemodynamic response function, the canonical HRF. As I mentioned earlier, that will assume homogeneity assumption. That assumption is that the curve is the same across the brain, regardless which region. That curve is the same shape across participants, across task conditions, right, across different age groups, patients, controls. We always use the same. Well, that's a strong assumption, but it works reasonably well for if you design experiment carefully and for those regions, for example, motor regions or visual cortex. But if we move away from those regions with a strong response, for example, prefrontal cortex, subcortical regions, that canonical HRF may give us some compromised results. Sometimes even biased, substantially biased, it will sacrifice in detection sensitivity. So can we do better than that? Well, because the assumption is strong for probably most of the brain regions, and also we take cross task, cross participant variability. So there's another approach. We take another extreme that we don't make assumption about the hemodynamic response shape, right? So instead we use the data to help us to decide what the shape looks like. So this is more, to some extent, assumption-free, not fully, but to some extent. So what this is about. So we use multiple basis functions like multiple rulers. The traditional approach, canonical curve, is a ruler too, but that ruler is pretty rigid. The shape is fixed. In this case, those rulers are put at each time point, right? So each time point, for example, put this, we in African call it a tent, or sometimes we call it stick functions. Why it's called a tent? The shape is like a tent, camping the tent, right? So you can see the shape. At the center point is the peak, then linearly it goes down to the beginning to the end. So it covers, for example, each TR, three consecutive time points. We put a center point, put a ruler, that's a yardstick there with a unity of 1, for example. Then set up a tent like this. So that's mathematically you can express the function like on the left-hand side. But we don't need to pay much close attention to that mathematical expression. Focus on this heuristic, graphic interpretation. Suppose we focus on 6 time points. We put it six rulers, or depends on how we count it. Put it one at the first, right? The 0, then the first TR, second, the third, all the way to 6. Put it, this would be 7, right? 7 rulers with a height of 1. But you don't say the 1, that's because we use that ruler to measure the data, right? The time series. At each trial, we use those 7 rulers to cover, 6 time points. In real case, of course, we will decide how much we want to cover the duration. But suppose we focus on 6 time points, we use those 7 rulers to search the data. Well, in each ruler at each time point, for example, the first time point at 0, presumably we would get 0, right? So at that point, at the beginning, there's no both signal, right? Well, ideally. So that would be 0. The second one, the first TR, there's some height. Then the second TR maybe reach higher, almost to the peak, right? So we use those 7 rulers to measure the data somehow. Then in the end, we get those 7 beta values. Those 7 beta values, they're really to magnitude to give us the profile of the hemodynamic response. So this green curve contains 2 pieces of information. One piece is about the shape, right? So in this case, we don't make assumption about the shape. In the end, we capture the shape, use the data to find the shape. That's one piece of information. Second of all, we can also tell about the hemodynamic response magnitude. That magnitude, one simple way is about the height of the peak. For example, in this case, well, we say it's roughly at the second TR. Right? So those 2 pieces of information are important. Even if you only care about the magnitude, the shape is also matters, right? Because if we use the canonical HRF, the peak always occurs at 5 seconds. We already know some burn regions, the peak occurs earlier than 5 seconds. Probably most burn regions, at least the empirical data shows the peak occurs ahead of 5 seconds. Some regions are around 5, but sometimes as early as 4 seconds or even slightly earlier. So that's one thing. Another thing, there's an undershoot. The SPM's canonical HRF, the undershoot is pretty shallow, but in reality, some burn regions, the undershoot is much deeper, right? Sometimes even as deep as the peak. Right? So there are a lot of much heterogeneity about the shape, the shape itself, in addition to the peak, the magnitude itself. So that's why this this approach, the estimation approach, is, in theory at least, is much more sensitive, right? Because we don't rely on that, use that rigid ruler. Instead, we use the data to estimate. Well, ideally, this would be, we should adopt this approach, right? But there's one, well, at least two caveats or two downsides or disadvantages. One is that you can imagine the model would be much more complicated, right? Before we could only, each task will create one regressor. Right now, we need multiple regressors. Each basis function, each tent would correspond to one regressor. So in this case, we need 7 regressors. So the design matrix would be much bigger, right? So 2 tasks, the canonical HRF will need 2 regressors. For using this would be 14 regressors. So the modeling process would be more complex. Whether and the second of all, would we be able to solve it, right? Because you may think this would be highly correlated because we're so jammed with many regressors. So that's a big concern. In addition, then in the end, each task will end up with multiple beta values. How do we summarize that information? Right? Before, it's just each task one regressor, one beta value, then we just directly compare them. Now we have multiple betas. How do we compare? When we go to group level, how do we say something at the group level? We compare 2 groups. Well, not just compare 2 numbers. We compare 2 curves. So those are the challenges. That's why the field mostly are stuck with this canonical HRF, but there are ways to handle the complexity, and that can help us substantially improve the detection sensitivity, which we'll cover later. But so that's and another downside is since we currently have a no effective way to constrain the shape, because mostly we rely on the data. So you can call it data driven to some extent, right? The only thing we constrain is about the duration, how much we want to cover. For example, cover 16 seconds, for example, right? That's the only thing we can constrain about this approach. In the end, we come up with the shape, the estimated hemodynamic response profile for each voxel, but since it's purely data driven to some extent, then we may end up with some funny shapes occasionally. That may occur, especially if there's a head motion, right? Synchronized, head motion especially synchronized with the task. That's one possibility that can contaminate the estimated hemodynamic response. So hopefully in the future, we can put in more constraint, improve the to avoid some of the problem. I mean, at least mitigate the problem, those caveats. So that approach, at least, it will increase to some extent the detection sensitivity. Let's look at a concrete example. Suppose we have this experiment with 10 rounds. This is the published paper. I don't remember, probably almost 20 years ago. So it's a task with it's a factorial design. So that's maybe use this slide to better demonstrate what the experiment is. So there are 4 different tasks. It's a 2x2 design. So it's either a category. One factor is either it's a human image or it's a tool. On the right side, it's a saw, right? So it's a tool. On the left hand is a human, the first column. Horizontally, the first row is a whale image. We can clearly see, but on the second row, the image is pretty vague, right? So you start the images. But it's better to visualize this through a movie, but so this is a still image. We cannot see, but if in whale scanning, this would be a moving, all the 4 tasks are moving. For example, even the human images so are moving. Those dots are moving, so you would be able to recognize it's either a human or tool. In this case, the lower right corner, this is a hammer, actually. So those are the tasks. 4 tasks is a 2x2. So it's either, I mean, category, right? So either human versus tool. Another factor is the image, whether it's a whale image versus dot image. So in this case, if we use the hemodynamic response estimation approach, we would create in this case, you cover 17 seconds. You can see at the top, the title here is cover 16 seconds. So we use, for example, 17 tenths, for example, right, from the 0 to 16th each TR. Oh, sorry, that's not exact because the 16 seconds, the TR is 2 seconds. So we would have probably, I don't remember, probably nine regressors, nine basis functions. So that's why you can see this design matrix in grayscale image. It's pretty messy. So the first, remember there are 10 rounds. Suppose we use quadratic polynomials. Each round will have 3 columns, 3 regressors. The first 3 columns are for the first round. So all the way, we have the first 30 columns are for the baseline and the drift. So in this case, the linear plus quadratic. So those are the first 30 columns. The last 6 columns are the estimated head motion components. In between, so there are 4 big chunks. Each chunk has multiple columns. In this case, about actually 7. I say 7 tenths. Maybe 9 actually in this case. So that's why you say this slanted patterns, because each basis function, each tenth shift 1 TR, right? So that's why you say there's a downward slope for each chunk. So that's why there's 4 big groups, because 4 separate conditions, but each condition will have 9 regressors. Each one corresponds to a time point for the estimated hemodynamic response profile. So we use that, we solve it, so you can see at each voxel. So here at the bottom, we show 9 voxels. Each of them, we can use those 9 beta values to characterize the estimated hemodynamic response. So instead of a single beta value for assumed hemodynamic response, in this case, we have the whole profile at each voxel. So that's the approach. We use the hemodynamic estimation approach. So this approach is much more powerful, more sensitive. So as I mentioned earlier, there are a couple of downsides. One is the model complexity. Second one is how to summarize the result, especially at group level, as challenging. We will cover that later. In between, there's a middle ground. So we don't have to double either. Maybe in SPM, especially, we can use 3 curves. Here, the red curve is the canonical HF that captures the main shape. So we make some adjustment. So for example, the blue curve, we shift the peak a little bit. Usually it's shifted earlier, right? So we know most brain regions, the peak occurs before 5 seconds. So the blue curve will help us capture the peak a little bit more accurate, right? The green curve is called a dispersion curve. That's the second derivative of the canonical HRF. What does that do? That helps us to change the duration of the peak to make it either narrower or wider, or fatter. Right? So those 2 auxiliary curves or basis functions help us to improve the fading. But the big problem with this approach, this is probably adopted in both across all software packages. FNU we have this option too, SPM, FSO. The big problem with this, in the end, people just throw away those 2 auxiliary basis functions. The beta values they throw away. They only focus on the beta associated with the blue curve, canonical curve. So that basically, at the beginning, you say, I want to improve the fading. But in the end, yes, the fading probably improved to some extent, even though not as good as the estimation approach. But you improve the fading, but the improved part you throw away, you still go back to the beta value associated with the red curve. So you try to gain something in terms of fading, but in the end, the gain is totally wasted. You still estimate the hemodynamic response associated peak at 5 seconds, because that's the beta you keep when you go to group level. So that approach on purpose should help us improve the fading, but in the improvement is fully thrown away, unfortunately. So I think I'm running out of time. I just briefly discuss a couple of issues. Multicollinearity, I think sometimes we worry too much, except it's a human error. You make some mistakes about the timing. As long as we explain the design experiment carefully, collinearity is not usually a big concern nowadays, I think. Even if it's highly correlated, uh, that I mean, on paper, you may say that's difficult, right? We may pay the cost in terms of standard error, the uncertainty, but it helps in terms of the trial sample size. So that's as long as you design experiment carefully, that should not be a big problem. The second issue I want to talk about is the residuals. The traditional statistical model, linear regression model, will assume the residuals are white. What do I mean by white? It means that there's no structure. They're totally, we assume it's totally independent with each other. But in reality, we don't do a good job in fitting the data because there's so much information in the from data we cannot explain. So that creates a problem. That problem is there's a temporal structure in the residuals, which we cannot explain. So the traditional approach called the ordinary square would be able to would not be able to capture that temporal structure. What it can do, what's the cost? The cost is basically the standard error, the uncertainty, the precision is inflated. But there's a way to handle that. That's Anthony, that's using the AMA model to capture that temporal structure. So lastly, I already discussed earlier about the multiple ones. So that's, I think, already discussed earlier. Why usually we can calculate multiple ones, create a single model instead of separate models for each one separate. Lastly, I want to say percent single change because this is definitely unique. This is associated with a preprocessing step called scanning. In SPM and FSL, the typical procedure is called grand mean scanning. So you divide each voxel's value by the whole brain's average cross time and cross space. So this is probably some heritage procedure from PET data, and let's stick to this procedure. The problem with this is about the interpretation. The beta values, if you adopt the grand mean scanning, the beta values are not interpretable. If that's the case, how do you go to group level? You want to say something about cross subjects if the betas are not interpretable. So in Anthony, the way we solve this problem, we adopt a local mean scanning. So each voxel is scaled by its own average cross time, not cross space. So of course, this is an approximation. In the end, the beta can be interpreted per single change. So that's there are two important aspects I want to emphasize. This is not just for interpretation, right? Not just to say we can interpret the beta as percentage. More importantly, if you read the neuroimaging literature, people don't report the beta values. So that's why, because if you adopt the grand mean scanning, the beta is not interpretable, that's one reason. And the downside, the long-term damage is that when we talk about reproducibility in the field, how do we assess reproducibility? We need to summarize across different studies. That is called meta-analysis. Meta-analysis, we do need the estimated effect magnitude. So we do need the beta values. But in current climate, the beta values are not reported, then we pay the cost in terms of reproducibility. Because cross studies, the betas are not comparable. How do we summarize them? We can only use the p-value statistics, but the statistic values are, information is compromised. It's not as fully, with both beta and t. So that's the reason we emphasize proper scanning, and then the beta can be interpreted per single change. So with that, I think I want to ramp up this session about the individual level affirmative data analysis. So that's, I think this basically summarizes what I talk about. So I want to stop here.
Great, thank you, Gang. I'm going to stop the recording for this.